Today, the student will be able to understand the transformations in each exponential function in order to create a graph. What it means by transformations, if we use transformations on a graph, that means they're going to move around the graph. So they're either going to move up or move down or move left or move right. Or yesterday, we talked about how sometimes graphs can stretch up or compress or shrink down. So we're just talking about taking the normal graph that we have and moving it around. So we're still looking at exponential graphs. So remember, our parent function is this b to the x. So if we take that initial graph and we multiply a number a, that's when we're going to get a stretch or compress, or sometimes it's going to reflect over the x-axis, okay? You haven't seen any of those yet. If we subtract a number h from x, so if we have a subtraction in the exponent spot, if we are subtracting, it's going to move the graph to the right, and if we add, it's going to move the graph to the left. If we have a number k that's added to the back end of our equation, if we are adding k, our graph will move up, and subtracting k, our graph will move down. The other thing you should have noticed yesterday, so yesterday in your discussion question, I talked to you about how some graphs look like this bottom one. From left to right, those graphs go down, but most of your graphs from left to right went up. And I told you that this, if they go up from left to right, is called an exponential growth, and if they're going down, it's an exponential decay. In the discussion question, I asked you to analyze and compare the equations. What you should have figured out is that if your b value is greater than 1 whole, you're going to get something that grows. You're going to get an exponential growth. If your b value is less than 1 whole, you're going to get a decay. Your b value will never be negative, so it will always be bigger than 0. Your a value can be negative, but your b value will not. So some of you wanted to flip the graph by making it negative across the y-axis, and that doesn't work. In order to get it to go to decay, you had a fraction like 1/4, or a number like 0.25, or 2/3. All of those b values made your graph decay instead of grow. So that's what you should have figured out in the discussion question yesterday. And when I looked at those, most of you had that. Okay, so this is really just like a large overview of how the graph will move, or how the equation will move around the graph. We're going to do some examples now, and we're going to find the actual points on the graph, and then I'm going to show you how we really could have used the movement instead if you wanted to. So let's look at this equation, y equals 3 to the x minus 2. Again, I just picked some random numbers in my tables. I use -1, 0, and 1. Let's figure out what the y values would be. So 3 to the -1 minus 2, that's really 1/3 minus 2. And 2 is really 6 over 3. So I have 1/3 minus, 6/3. So I have 5/3. So I have the point -1, -5/3, my bad. Okay, -1, -5/3. That's really like -1.7. So let's put a point at -1, -1.7. So -1 whole and more, about there. Okay. Now, if x is 0, then 3 to the 0 power minus 2. Remember, anything to the 0 power is 1 whole. Minus 2 is -1. So we have a point at 0, -1. All right, then 1. So 3 to the first power minus 2 is 3 minus 2, which is 1 whole. So I have a point at 1, 1. Okay, now we know we have something that goes like this, but we need to figure out our asymptote. So let's pick another negative number to see if we can figure out how far it's really going down. So if I use -2, then I have 3 to the -2 power minus 2. So that's really 1 over 9, because remember the negative power just makes it a fraction, and 3 squared is 9. Minus 2 whole is really 18 over 9. So that's -17 over 9, which is in decimal -1.8. So it's a little bit further down from -1.7. Okay, let's pick one more. If I use -3, then 3 to the -3 minus 2, 3 to the negative 3 is 1 over 27. Minus, if I change 2 to something over 27, it's 54 over 27. So I'm really looking at negative 53 over 27, which is negative 1.96. So that's almost negative 2. So what we can tell from this is that our graph is getting really close to negative 2, but remember there's an asymptote, so it's never actually going to touch it. So our asymptote this time is at x equals negative 2. Yesterday they were all at x equals 0, okay? So that's our graph. So let's talk about the domain. Your graph still runs forever left and forever right. So our domain is still negative to positive infinity. Now the range always goes from the asymptote. So our lowest spot is at negative 2, but it doesn't touch negative 2, so that's why we use a parentheses, but it goes all the way to infinity. The asymptote is at x equals negative 2 because it's approaching that. Negative 1.96 is really close, but it will never touch it. Our y-intercept is at 0, negative 1. Okay, so we can use the table to find the graph, or we can take the parent function part of the graph and see how it's moving. So if I look at just the parent function part, if I look at 3 to the x power, if I graph that, then I know that I cross the y-axis at 1, and then I have a point at 1, 3, just like we did yesterday. Okay, I also know there's an asymptote at x equals 0. So the graph looks like this. Okay, now, if you compare those two graphs, what really happened is when we take minus 2, we are subtracting something from the back end of that equation. So it's like when we have this k piece. So if we subtract k, then we are moving down. So if you graph the original and you move 2, if you're asked how would the graph translate from the parent function, you're going to say that the graph translates down 2. Translates down 2. The other thing we can tell is because the b value is greater than 1, then we can say that this is going to be an exponential growth because of the 3. Okay? So it translates down 2, that's because the minus 2 in the back, and it's growing because the b value is a 3. Okay? Okay, so now we know how to just blindly graph that equation, but we also know how to compare it to the parent function. Okay, next. If y equals 2 to the x minus 1. So let's figure out these values. So again, I just use negative 1, 0, and 1. So we have 2 to the negative 1 minus 1 power is 2 to the negative 2, which is really 1 over 2 squared, so it's 1/4. Okay? All right, then to the 0, so we have 2 to the 0 minus 1 is the same as 2 to the negative 1, which is 1 over 2, so it's a half. If I have 1, then I have 2 to 1 minus 1 is 2 to 0. Anything to the 0 power is 1 whole. Okay, so let's plot these. We know negative 1, 1/4. It's about there. We know 0, 1/2. Oops, back. Okay, then we know 1, 1. All right, now let's pick a couple more. So let's do 2. So 2 to the 2 minus 1 is the same as 2 to the first power, so it's 2. So at 2, we have a point at 2. Then at 3, we have 2 to the 3 minus 1 power, so 2 squared is 4. So at 3, we're at 4. Okay, so I'm pretty confident to say that this is my graph. Okay, the domain goes all the way left and all the way right. The range goes from 0 to infinity because the asymptote is at x equals 0. So we are approaching 0, but we'll never touch it. Okay, the y-intercept happens at 0, 1/2. Okay, now that's how we just blindly get that equation, but if we wanted to compare it to the parent function, our parent function on this one is 2 to the x power. So I know that gives me a graph where I have a y-intercept at 1, and I have the ordered pair 1, 2. Okay, now if I take this graph, okay, this graph kind of looks like it goes down, but it doesn't really. What it's really doing, and when I have the -1 in the exponent spot, and we look back up here, so we're subtracting 1 up here, that's h. When we subtract 1, we're moving the graph to the right. So really, if you started with its parent function and you moved all of the points to the right, one value, then you'd end up with this new graph, okay? All right, number 3. Number 3, if you're using the document that was originally posted, it had this equation, -6 times 1/3 x minus 2. We're not going to use that one. Instead, we're going to use f of x equals -2 times 1/2 to the x power minus 2, okay? So let's build a table. So -1, 0, and 1 is just always a good place to start. All right, so I have -2 times 1/2 to the -1 power minus 2. Okay, you have to remember PEMDAS. When you use PEMDAS, you have to do the exponent first, and then you can multiply. So I have -2, 1/2 to the -1st power is really a whole number 2, because remember the negative exponent flips your fraction. So instead of 1/2, I have 2/1, and then minus 2. So 2 times -2 is -4, minus 2 is -6. So I have an ordered pair at -1, -6. Okay. Then I have, then at 0, so I have -2, 1/2 to the 0 power minus 2 is -2 times 1 whole minus 2. So -2 minus 2 is -4. So at 0, I'm at -4. Okay. At 1, -2, 1/2 to the 1st power. So that's really -2 times 1/2 minus 2. -2 times 1/2 is -1. Minus 2 is -3. So 1, -3. Okay, now, I know that I have this kind of curve, and it's weird because it's upside down over the x-axis, but I'm not really sure where my asymptote is, so I'm going to choose a couple more numbers. So let's use 2. So -2 to the 1/2 squared minus 2. So that's really -2 times 1/4 minus 2, which is really -1/2 minus 2, which is going to give me -2.5. So at 2, I'm in -2.5. Okay, so then at 3, I have -2 1/2 cubed minus 2, which is really -2 times 1/8 minus 2. And when you simplify that, you get -2.25. So I'm at 3, -2.25. So I'm pretty comfortable now saying that my asymptote is at -3, because I'm getting closer to that, but it doesn't seem that I'm ever actually going to touch it. So I have this graph here. Okay, now, there's a lot of things going on with this graph. So let's graph the original so we can compare. If I have 1/2 to the x power, then I know that I have a point at 0, 1. Or, come on, man. Okay, 0, 1. And then I know I have a point at 1, 1/2. So this is an exponential decay. And looks something like this. Okay, now, in order to get from that green original parent function of exponential decay to the new purple function that's being translated and moved all around the graph, quite a few things happened. First of all, the -2, that's an A value. And what it did is it reflected across the x-axis, and it also stretched my graph out a little. So it made it a little bit steeper. And you can't see that very well because we graphed by hand, but just the graph is steeper because 2 is a larger number, okay? Then we have the 1/2 is what told us that we have an exponential decay. Because if the b value is less than 1, you're decaying. Then the -2 at the end tells us that we translated the graph or moved down 2 units. So if you think about first reflecting this graph, so you flip it over the x-axis, you stretch it a little bit, and then you move it down 2 spots. That's how we created from green to purple. Okay, so if you know the equation, you can make a table and you can just graph it. If you know the parent function and you want to know what's going to change about it, then that's when you can use these notes up here to figure out where it's going to go. Okay, all right. Let's do, so we need the domain, the range, the asymptote, and the y-intercept. So the domain, it still goes forever left and right. The range is a little bit different because the lowest this graph goes is -infinity. And then the highest it goes is -2. So that's kind of reversed from what you're normally thinking with range. The asymptote we figured out is x equals -2 because we moved down 2 units. The y-intercept happens at 0, -4. And that's it.